In this video, we are going to solve a second-order ordinary differential equation. We're going to use as an example the mass spring damper system that we developed in a previous video, for example, as you might find in an automobile suspension system. For this system, we have a mass that is supported by a spring with spring constant K, and it's also affected by a viscous damper with a damping coefficient that we've called sigma. The position of the mass is defined as x of t from its equilibrium position, and we also can have an input which we call u of t, which is, for example, in an automobile would be the position of the axle as it moves up and down as you travel down a bumpy road or similar. Now we developed the differential equation, which has this form: m times the second derivative of x with respect to t plus sigma times dx dt plus kx is equal to the forcing terms, which are k times u plus sigma times du dt. In this particular video, we are going to deal with the corresponding homogeneous problem, which is where we set the forcing terms on the right equal to 0. To solve this kind of equation, we do as we always do with our differential equations, and we assume a form of a solution. In this case, we assume a solution to have the form a, some constant a, times e to the lambda t. By substituting this assumed solution into our differential equation, we can determine what lambda has to be in order to find our solution. To do this, we'll need to know that dx dt is equal to a lambda e to the lambda t, and we'll need to know that the second derivative of x is equal to a lambda squared e to the lambda t. When we substitute these into our equation above, we get m times the second derivative, which is a lambda squared e to the lambda t, plus sigma a lambda e to the lambda t, plus k a e to the lambda t, all of that equal to 0. Remember, we're setting the forcing terms equal to 0 in this particular case. Now e to the lambda t can never be 0 no matter what lambda or t are, so we can divide through by e to the lambda t on the left-hand side. A could theoretically be 0, but that would lead to a rather boring solution, since our solution would be x equals 0 for all time. So we're looking for a non-zero case for a, so we can go ahead and divide through by a on the left-hand side as well. Now we can rewrite the equation as m times lambda squared plus sigma lambda plus k equals 0. This is known as the characteristic equation for our differential equation, because it determines what the value for lambda is, which in turn will determine what the nature or what the character of our solution will look like. To find lambda, we use the quadratic formula, which gives us lambda is equal to, if we think back to when we first learned the quadratic formula, we had coefficient a, coefficient b, and coefficient c, and so it's equal to minus b, which in this case is sigma, plus or minus the square root of b squared minus 4 times ac, so we get 4 times mk, all over 2 times the coefficient a, which in this case is 2m. Or we can rewrite this as lambda equals minus sigma over 2m plus or minus the square root of sigma over 2m squared minus k over m, where I've just gone and taken the 2m and multiplied or squared it and brought it under the square root sign and substituted through like that. Now the solution to this equation is dependent on the nature of the terms underneath the square root sign. If, for example, the terms under the square root sign are, I'll write a little square root here, if the terms are greater than 0, then we'll get real roots to our equation. If the terms under the square root sign are less than 0, we'll get imaginary roots to our equation. And if the square root sign, the terms in the square root sign are equal to 0, we'll get repeated roots. And each one of these cases will lead to a solution that has a different form than the other ones. So let's start off by looking at the case where we have imaginary roots. And further, let's look at the degenerate case when sigma is equal to 0. That is, we have no viscous damping to our system whatsoever.